Welcome back to the classroom. My name is Mr. Wong. So in the previous video, we went through the setup of motions on inclined planes, how to perform that experiment. Given that we've already got the experimental data from last recordings, we are now going to try and graph it out, and we're going to plot acceleration over sine theta from the rearrangements. As you can see, will give us acceleration due to gravity from the gradient.
Alright, so let me just show you what we have so far, just using that simulation there. This is just another different set of data that I've used. So if you got it from the simulator, then keep up using that. Different angles from angle 17 degrees all the way to 19.8. I've also ensured that the displacement stays the same. That way I can work out what acceleration is, because if you recall at the start of the lesson, we said that acceleration is 2s over t squared. So I'll just put those numbers in there. You'll need to know what sine theta is, and you'll also need to work out the average time of each interval. So these are some of the questions that you'll need to answer. It says identify the independent and dependent variable. That's actually given by this question 3 here. It asks you to plot a graph of acceleration versus time. Now, acceleration versus time, that already tells you the variables you're looking at. Okay, so what was the thing that we were changing? That's what the independent variable means. Okay, in the experiment, we were changing the angle of our ramp. So sine theta was actually our independent variable. If you really want to write it out, angle of ramp. Our dependent variable, that would be the acceleration forwards or acceleration down the ramp. Okay, I'm going to go through some of these other questions bit by bit, but for now, let's just work on this. Okay, so this is what we have. This is the graph. I am expecting you to do this on Excel, so I'll go through how to do it on Excel as well. What you have here is the vertical axis. Another way of calling it is the y-axis, and then we have the x or the horizontal axis. Can you please make sure that the vertical axis is where we put our dependent variable? So the thing that we were trying to measure was acceleration. So make sure you have acceleration. Please ensure you have the correct units. Sine theta down here, and because it's measured in degrees, you put degrees here. Now, a lot of you might ask, how do we do the graph? Contrary to maths, you don't have to start at 0. So let's say for sine theta, I don't want to start at 0. I want to start at 0.2. Let's say I want to start at 0.2. Okay, so long as I have my arrow or my little line to indicate I'm starting at 0.2, everything's good. And then just make sure you increase everything by small little increments. So maybe we'll increase it by 2.5 here, and then 0.3 like that. So same increments every time for every box we use. Let's say, for example, I start off at 0 here, but I don't really want to go to 0. Or I don't really want to use 0. I want to use a different scale after that. And then this goes to 0.05. Okay. If I want to ignore the 0 and just say this is where I really want to start from, you can do that squiggly line. So it just says there's a disconnect between the data. You don't have to worry about it. And then you just try and fill up about 80% of the graph. This is what I got on Excel. And we just basically plotted sine over acceleration. So let me just go through what that actually means. Your gradient is rise over run. The rise in this case is acceleration. The run is sine theta. Now, if you recall, we said that when an object is going down a ramp, okay, its forward force is a component of gravitational force sine theta. If I rewrite that, ma forwards equals to mg sine theta. Because the masses are the same, they cancel each other out. And then we're left with acceleration forwards equals to g sine theta. If I swap the equations around, acceleration over sine theta, I get the acceleration due to gravity. And so that's what my gradient value is telling me here. This is my gradient value. It's saying to me my acceleration due to gravity is 11.621. But if I compare that with obviously the accepted value, which is about 9.8 meters per second squared on Earth, there is a little bit of a discrepancy that I won't lie about. There is a slight discrepancy there. But that's essentially how we can work out the meaning of our gradient value is look back at rise over run, tells us acceleration over sine theta, and we look back on the theory that we wrote about early on, and we find that that actually tells us what the acceleration due to gravity is. For those who aren't sure how to graph this on Google Sheets, I'll try and make a video on it as well, but for now I just want to go through the data analysis. So the next bit is obviously trying to understand the errors. So like, what's the error percentage? If we look at this, accuracy, the definition of accuracy is the exactness of the measure. How close is the experimental value to your expected theoretical value? Now we already have the experimental value. That's what our gradient was for. The theoretical value is basically, in science, it's essentially you going to some kind of well-known source and work out what the number should actually be. And with gravity, the acceleration due to gravity, we all know it's 9.8 meters per second squared. If I want to work out the error percentage, this is the formula we use. Do not ignore the absolute values. It is on your calculator. So when you're typing it out, it should be using ABS. So you should have ABS accepted value, which is 9.8, minus your experimental value, in my case, was 11.62 over 9.8 times 100. That 100 there is just to give it into a percentage. So my error percentage is 18.57. So that's not ideal. You want your percentage to be closer to about, or closer to 5% or less. But that's what I got. Just for those who want to look at what reliability validity is, reliability is, was the measurements consistent? So was the timing the same each time? If I look at my one and see if I got a linear trend, you could see that from about 29, so sine theta here, to my first 5 trials, it's a relatively linear path. So you can see that the trend, not only the time was consistent, but the trend is consistent to each other as well. So that's really good. Though, unfortunately, you do see it slightly deviating away in the last 3 points. So it does kind of disperse away. That could be a reason why the trend is obviously not as linear, and that could be where the error kind of came into at this bit here. The other thing is, if you do have an issue where a point looks like it's really far away from your overall trend, you can just circle that, highlight that, say that's the outlier, and you can disregard that when drawing your line of best fit. Validity, so that's to say that all the variables are kept the same apart from the one you're investigating. The one that you're investigating is obviously the independent variable, which is the angle of the ramp as you do the experiment. So only one independent variable and the rest is controlled. That's how you would ensure that it's a valid experiment. Another thing is if you repeated the experiment, that also ensures that it is valid. But it doesn't work quite the same way around. So just because the experiment, or if the experiment is valid, it's also reliable. But if it's reliable, it doesn't necessarily mean it's valid because you still have to ensure the variables are kept under control. The last bit I'd talk about is just writing a conclusion. There are 3 components when writing a conclusion. We call the first step the claim. So what were you trying to investigate? Write a statement that answers that question. Okay. And what we were trying to investigate was the angle of an inclined plane. How does that affect the acceleration of our object? So what does that say? Just a statement. Increase the angle of an inclined plane to horizontal. So increasing the angle of the inclined plane to the horizontal will increase the acceleration of the object on it. So that's my claim, right? It's just a statement to answer whatever I was thinking about investigating, whatever my scientific aim was. The claim, the opening statement, needs to pinpoint that part and answer it. Next part is the evidence. So any observations and results you recorded from the experiment. What did I say here? From the experiments, the relationship between A and sine theta is directly proportional to each other. At 17 degrees, the trolley accelerated at that, whilst at 19, accelerated at that. So that's just me referencing that they are directly proportional to each other. You could also mention as part of the evidence is as you increased the angle of incline, the object essentially traveled the same distance at a shorter period of time. So that's what you could say. An increase in sine theta or increase in theta, increased acceleration down the ramp. And so what's the justification that you can make out of this? So this is where you kind of relate back to the formula you use. So we said that the acceleration going forwards or going down is proportional to sine theta. Okay. This, you can read it out yourself. It's pretty self-explanatory, but I want to just highlight why it gets bigger. Remember, at a really tiny angle, okay, at a really tiny angle, F forwards, or maybe just to make it easier, our acceleration is just a fraction of g. Because sine theta, when is sine theta at its maximum and minimum value? When sine theta, or when theta is at 90 degrees, so perpendicular, that's where you have maximum value of whatever you're looking in. If sine theta and theta is at 0, so it's parallel, that's when it's at its minimum. So when my trolley is somehow being dropped at 90 degrees, that is exactly the same value as fg, because that maximum is 1, minimum 0. That's why you have no effect if it's just on a flat surface, because the angle is 0, sine theta is 0. G would have no effect on whether or not this has an forward acceleration or not. So
Alright, if you're listening to this video up till this point, thank you so much for listening through. Hopefully that gives you a better understanding of how to analyze, plot out the data we've shown, and find the acceleration due to gravity that's acting on our inclined plane. I'll see you next time. Thank you for listening once again.